It's a big surprise. Nobody thought the ocean was this deep. So all of a sudden we've got scientists saying, why is that?
For all our focus on the sky, the deepest water on Earth is hiding a far bigger problem. A probe dropped near the Puerto Rico Trench recorded a temperature jump that should not be possible.
Is it a little hole? Is it a big hole? What kind of feature is it down there? There's a whole lot of questions you get when you find this one spectacular reading.
It shot from freezing to blazing in a single instant, and then vanished without a trace. The reading was quietly pushed aside, but it leaves one question that no one can shake. What in that darkness can unleash heat like that? Unexpected energy in the deep. At the bottom of a trench like Challenger Deep, the seafloor sits at around 36,000 feet below the surface. The weight of the water there adds up to roughly 16,000 pounds pressing on every square inch. The temperature hovers just above freezing, yet the water stays liquid because of the huge pressure. No daylight reaches that far, and storms at the surface barely matter. On paper, it looks like one of the most steady and boring places on the planet, the last place you would expect to see a wild jump in temperature. Because no person can go there unprotected, we send down machines that can listen and measure. One main tool is a hydrophone, an underwater microphone that turns tiny pressure changes into signals. Another is a CTD, short for conductivity, temperature, and depth, which records how salty, how warm, and how deep the water is. Some of these sensors hang on long moorings or heavy freefall frames that sink to the bottom and later rise back up so we can read what they saw. In the middle of the last decade, a team from the United States National Oceanic and Atmospheric Administration and Oregon State University lowered a full ocean-depth hydrophone into Challenger Deep. It fell for hours, settled on the bottom, and recorded for several weeks. When they brought it back and listened, they heard constant noise, earthquakes, distant storms, ship propellers, and whale calls from many miles away. The deepest known point in the ocean sounded more like a busy intersection than a graveyard. The main reason that spot is such a good listener is that sound behaves very differently in water than it does in air. In air, sound moves at a bit over 1,000 feet per second. In seawater, it travels about 5 times faster and can go much farther before it fades, because water is dense. There is also a natural deep sound channel, a layer where temperature and pressure make sound bend back toward the middle instead of escaping. A loud noise in that layer can travel thousands of miles with only a slow loss of strength, so one hydrophone can hear events across an entire ocean basin. Many of the deep listening posts we have today grew out of old military systems. During the Cold War, the United States Navy built long lines of underwater microphones across parts of the seafloor to track the low rumble of distant submarines. Later, parts of that network, along with new listening stations, were turned towards science and used to record the ordinary noise of the deep ocean. Once researchers started to comb through those recordings, they found many sounds that did not match anything people expected to hear. One famous example is the signal known as the bloop, recorded in the late 1990s in the South Pacific. It was very low in pitch, but so loud it was heard more than 3,000 miles away, which made people think of some giant animal. Later, scientists compared it with sounds from icebergs cracking and scraping along the seafloor and found an almost perfect match, so today it is treated as an icequake, not a monster. Other signals with names like upsweep, Julia, train, and bio-twang have since been tied to moving ice, undersea quakes, or the calls of large filter-feeding whales. Our ears in the deep ocean are sensitive, and so are our thermometers. A modern CTD, or a temperature sensor on a mooring, can detect changes of only a few thousandths of a degree. Near the trench floor, where the water is normally cold and steady, the readings should form a flat line for long stretches of time. When that line suddenly jumps, even by a tiny amount, everyone in the control room pays attention. The pressure down there leaves almost no room for equipment mistakes. The housings around sensitive electronics are working against forces that could crush a car. When a readout jumps from a steady near-freezing value up to a much warmer number and then falls back again, the first question is whether the probe passed through a pocket of warm water or brushed something hot. The second question is whether something on the seafloor just changed in a sudden, violent way. The fear comes from how little of this hidden world we actually track. Down there, we are not just logging numbers from empty water. We are listening to something that moves and dumps energy into the dark. To see what can survive in that noise and pressure, the next step is to look at the creatures that treat 7-mile depths as home. Life under crushing pressure. At the very bottom of the deepest trenches, the weight of the water is so high that every square inch of your skin would feel more than 8 tons pressing down. That is like balancing several full-grown elephants on a postage stamp. Yet in that same pressure, cells still divide, muscles still move, and soft bodies drift over the mud. For any normal cell, that depth is pure damage. The tiny tools inside every cell, called proteins, only work because they are folded into very exact three-dimensional shapes. High pressure tries to force extra water into those shapes and crush them flat. The thin, oily skins that hold cells together can also turn stiff and leaky. If you took a shallow water fish and somehow moved it instantly to trench depth, its chemistry would fail long before its bones ever cracked. Deep-sea fish fight back with chemistry. Inside their bodies, they stockpile small helper molecules that act like braces around each protein. One of the most important is called trimethylamine N-oxide, usually shortened to TMAO. It's the same substance that gives strong-smelling fish their sharp, fishy scent. In deep fish, the amount of TMAO in the body increases as the water gets deeper. Lab work that measured TMAO in many species shows a steady climb from shallow fish down to those from almost 16,400 feet, and then keeps going for true deep-sea types. When researchers take those real measurements and extend the line downward, they hit a hard wall. By the time you reach about 27,000 feet, a fish would need so much TMAO to protect its proteins that its body fluids would be saltier than normal seawater. At that point, water would start rushing into the cells instead of staying balanced, and the animal would not survive. This is why some biologists say there is a chemical ceiling that stops bony fish from living much deeper than the upper part of the deep trenches. Even so, some species push right up against that limit. In recent years, a team from Japan and Australia filmed a small pale snailfish in the Izu-Ogasawara Trench, south of Japan, at a depth of about 27,350 feet. That is the deepest fish ever seen alive so far. A few days later, the same project caught related snailfish in traps in the nearby Japan Trench at about 26,340 feet, making them the deepest fish ever brought to the surface. These snailfish do not look like tough animals at all. They are small, soft, and almost jelly clear. They have thin bones, no heavy scales, and bodies that are mostly water and gel rather than dense muscle. Studies of related snailfish from the Mariana Trench show extremely high levels of TMAO and even extra copies of genes that help make it as if their whole bodies have been rebuilt around this one job of holding proteins together under pressure. So far, though, no one has confirmed a fish right on the floor of the deepest point of the planet. Below those snailfish, something else takes over. Microbes reach places where fish cannot. In mud from the very bottom of Challenger Deep, scientists have grown bacteria that refuse to divide unless the pressure is cranked up to values that would crush normal lab equipment. Some strains in the genus Moritella grow best around 10,000 to 11,600 pounds per square inch, similar to what you get at depths beyond 32,800 feet, and will not grow at all near surface pressure. These pressure lovers tune the fats in their cell membranes and the shapes of their proteins so that everything stays flexible and active instead of locking up. For a long time, people thought there could not be much variety down there. Recent work has blown that idea apart. In 2025, an international team sampled sediments from several trenches between about 3.7 and 6.8 miles deep, including the Mariana Trench. They reported thousands of microbial species that had never been seen before, many with gene sets that do not match anything from surface waters. These microbes form an invisible film over the mud and inside it, turning even the darkest trench floor into a busy factory of slow, quiet chemistry. On top of that film, the larger animals crawl and swim. At trench depth, you can find sea cucumbers that look like pale slugs with frilled legs, segmented worms, and strange single-celled giants called xenophyophores that build fragile shells from surrounding grains. Amphipods, which are shrimp-like crustaceans, are everywhere. Many of these animals are mostly water and jelly inside with very little hard shell. That is not a weakness. By letting high pressure pass straight through their bodies instead of fighting it, they avoid the crushing stress that would snap a rigid skeleton. Some of these trench animals are huge compared with their shallow cousins. This is part of a broader phenomenon known as deep-sea gigantism, where certain invertebrates in cold, high-pressure waters grow significantly larger than their counterparts near the surface. One of the best examples is the supergiant amphipod, Alicella gigantea. Most amphipods are no longer than your fingernail. Alicella can reach about 13 inches long, roughly the size of a small loaf of bread, and lives at depths from around 15,000 to more than 23,000 feet in trenches and fracture zones around the world. No one fully agrees on why these deep crustaceans get so large, but a few ideas keep coming up. Cold water slows down chemistry in the body, so cells can afford to be bigger and still work. a large body can store more fat for long famine periods and can swim farther between scattered food sources. A big size can also keep them off the menu for some predators. Studies of Allicella show that it has extra breathing structures to pull more oxygen from the water, which may help fuel that big frame in such a low-energy place. Food is the real puzzle. Sunlight does not reach more than a tiny fraction of the ocean's total depth, so life in the trenches has to live off whatever falls from above or leaks up from below. The slow, steady background supply is called marine snow. These are tiny flakes made from dead plankton, bacteria, poop, and bits of organic dust that drift down from the sunlit surface layers. Most of those flakes are eaten or broken down long before they reach several miles down. What reaches the deepest trenches is just the leftovers of leftovers, spread out over huge areas. Every now and then, though, the deep sea gets a jackpot. When a large whale dies and sinks, its body can weigh tens of tons and deliver more food in one event than the surrounding seafloor would normally see in many years. First, big scavengers strip off the soft tissue. Then smaller worms, crustaceans, and snails move in and burrow through the enriched mud for months or years. In the final stage, special bacteria break down fats trapped inside the bones and release sulfur compounds. Those chemicals feed yet another community of clams, mussels, worms, and snails that can keep living on the skeleton for decades. A single whale fall can support more than 100 species and act like a small island of life on an otherwise bare plain. Some deep communities hardly use falling food at all. At certain spots where fluids rich in hydrogen sulfide or methane leak out of the seafloor, microbes build their whole lives on chemical energy instead of light. These bacteria and archaea take those chemicals, add carbon dioxide and oxygen, and make sugars in a process called chemosynthesis. Many of them live inside larger animals. Giant tube worms, clams, and some snails at vents and seeps have no working mouth or gut in the usual sense. Instead, they pack their bodies with symbiotic bacteria and farm them for food. Until recently, most of these chemosynthesis-based communities were known from mid-ocean ridges and relatively shallower slopes. In 2025, dives in the Kuril-Kamchatka and Aleutian trenches in the northwest Pacific found dense fields of tube worms, clams, and other animals built on chemosynthetic bacteria at depths of more than 31,000 feet. That is almost 1/4 deeper than any such community had been seen before. Even in places that do rely on sinking material, the link to the surface is tighter than you might think. In the late 1950s and early 1960s, nuclear bomb tests in the atmosphere flooded the air and surface ocean with an extra dose of a radioactive form of carbon called carbon-14. Decades later, scientists measured that same bomb carbon signature inside amphipods living in the deepest trenches of the Pacific, including the Mariana. That tells us that these scavengers are eating organic matter that started life near the surface, sank, and reached them within a human lifetime. It also suggests that their own tissues change slowly, and that some individuals may live for more than 10 years in the dark. Under that thin layer of mud and microbial film, the crust is bending, grinding, and sometimes tearing open, sending pulses of heat and chemicals upward. That restless engine under their feet is the same force that sends those sudden bursts of energy into the water that our instruments keep tripping over. The deep ocean's violent core. At the very bottom of the ocean, the ground itself is the biggest threat. An ocean trench forms where one huge plate of seafloor starts to sink under another plate. This kind of boundary is called a subduction zone, and it runs like a scar along parts of the Pacific and Atlantic Oceans. The plate that sinks is old, cold, and dense. The plate that stays on top gets bent and scraped. This slow collision builds up stress. When it finally slips, the result is an earthquake, sometimes a very powerful one. These same zones also feed chains of volcanoes that sit in arcs near the trenches, like the island arcs in the Western Pacific and the Lesser Antilles in the Caribbean. The shape of the trench, the steep inner wall, and the long curve that often matches a line of volcanoes are all signs that the planet is grinding its own crust back down into the deep mantle. That slow grind sets up a second kind of violence that you never see from the surface. Cold seawater seeps down through cracks in the ocean crust near these plate edges. As it sinks, it passes rocks that are warmed by rising magma. The water heats up, picks up metals and chemicals, and becomes a hot, dense fluid. Because it is now lighter than the rock around it, it rises back toward the seafloor and bursts out of vents. These are called hydrothermal vents, and they can push out water that is hotter than 700 degrees Fahrenheit. At those depths, that water does not boil into steam because the pressure is so high. It stays liquid, but it is far hotter and more corrosive than the near-freezing seawater around it. When this super-hot fluid hits the cold deep water, it suddenly cools, and the dissolved metals fall out as tiny particles. That is how black smokers form. Tall chimneys made of metal-rich minerals, venting clouds of dark fluid that look like smoke. Around them, you also get shimmering plumes where temperature and salt levels change the way light bends through the water. To most people, the deep ocean sounds like one unbroken block of cold water, but around these vents it is full of sharp edges. You can have water just above freezing only a short distance from pockets that are hot enough to destroy metal if the two ever meet for long. Instruments that pass through one of these plumes see sudden jumps in temperature and chemistry because the vent fluid cuts through the background water like a hidden jet. One of the strangest places on the seafloor sits on a submarine volcano called Daikoku Seamount, part of the Mariana Volcanic Arc. At the summit, explorers found a small crater filled not with water, but with a pool of liquid sulfur, often called the Sulfur Cauldron. It was first discovered in the mid-2000s during a National Oceanic and Atmospheric Administration Ring of Fire cruise. Later dives using remotely operated vehicles showed a dark, bubbling surface, where the molten sulfur moved like a thick metal liquid, sometimes giving off small bursts that looked like slow-motion splashes. The measured temperature of this pool was close to 370 degrees Fahrenheit, and nearby fluids were even hotter. What makes that sulfur lake so strange is the way it stays molten while sitting under thousands of feet of cold ocean. The key is constant heat from magma rising under the volcano, combined with high pressure and the chemistry of sulfur itself. Sulfur melts at a much lower temperature than rock. Heat from below keeps it just above that melting point, while the heavy water above acts like the lid on a pressure cooker. Instead of boiling away, the gases and fluids are trapped, and the sulfur stays in a liquid state inside the crater. Fresh gas and hot fluid keep moving through, so the pool can keep renewing itself rather than freezing into a solid sulfur plug. Far away in the Atlantic, another trench shows how warped the deep crust can get. North of Puerto Rico lies the Puerto Rico Trench, the deepest point in the Atlantic Ocean. Its deepest spot, known as Milwaukee Depth, reaches close to 27,500 feet, more than 5 miles down. When scientists mapped the gravity field over this trench, they found something odd. Gravity is not exactly the same everywhere on Earth. It changes slightly depending on how mass is arranged inside the planet. Over the Puerto Rico Trench, the free air gravity anomaly is strongly negative, meaning gravity there is weaker than expected from the surface shape alone. To explain that low gravity, researchers model a deep, dense slab of old ocean crust that is broken off and is hanging beneath the trench, pulling the region down. That same structure helps explain why this area can host large earthquakes and why the trench is so deep for its position. In simple terms, the crust here is not a flat sheet. It is bent, thinned, and loaded with chunks of rock sliding into the mantle at odd angles. The way mass is arranged under these trenches is enough to twist gravity, change sea surface height by small but measurable amounts, and store a lot of stress that can be released without warning. On top of the long-term plate motion and vent activity, the slopes of trenches can fail in sudden, brutal ways. When enough loose mud and sand pile up on a steep underwater slope, a big earthquake or even a smaller shake can trigger a huge underwater landslide. When that happens, the mix of water and sediment starts to move downslope under its own weight. This kind of flow is called a turbidity current, and you can think of it as an avalanche made of liquid mud. These currents can travel for hundreds of miles along the seafloor, staying fast and dense as long as the flow keeps picking up more sediment. One of the best-known cases happened off Newfoundland in November of 1929. A strong earthquake on the edge of the Grand Banks shook a thick pile of old glacial sediment on the continental slope. That sediment let go and rushed downslope as a massive turbidity current. As it raced across the deep sea floor, it snapped a string of undersea telegraph cables in sequence. From the timing of those breaks, scientists later worked out that the flow was hundreds of feet thick, moved at speeds of roughly 40 to 45 miles per hour, and carried on until it had dumped close to 175 cubic kilometers of mud, silt, and gravel across the abyssal plain. On land, that same event sent a tsunami into nearby bays and killed people along the coast of Newfoundland. More recent work shows that these flows are not rare quirks from the past. In the Congo Canyon off West Africa, instruments and cable breaks have recorded turbidity currents that traveled more than 600 miles along a deep channel, at speeds between about 8 and 17 miles per hour in some cases. This is the engine room behind those heat bursts and chemical spikes that instruments catch from time to time. Into that unstable landscape, we keep lowering delicate machines made of glass, electronics, and metal frames. What happens when those machines meet this tearing, venting, sliding world is where things start to feel much more personal. Our fragile machines versus the abyss. Every time a machine goes down towards 7 miles deep, the question is not only what it will see, the real question is whether it will come back at all. The first time humans dropped into the deepest trench, they did it in a steel ball bolted to the bottom of a huge floating tank. In January of 1960, the bathyscaphe Trieste carried Jacques Piccard and Don Walsh down into Challenger Deep to roughly 35,800 feet under the Pacific. At that depth, the pressure on the hull was more than 1,000 times the air pressure at sea level. One of the outer windows cracked on the way down. They stayed on the bottom for only a few minutes, saw a small flat fish-like animal on the mud, and then dropped ballast and went back up. That was the best technology the world had at the time. More than 50 years later, in late March of 2012, filmmaker James Cameron went back alone in a sub called Deep Sea Challenger. He rode down inside a narrow vertical capsule with walls only a few inches thick, tested to handle more than 16,000 pounds per square inch of pressure. His dive reached about 35,760 feet, again close to 7 miles down, and he spent several hours on the bottom taking samples and video. Since then, a newer two-person sub called Limiting Factor has made repeated dives to Challenger Deep and to the deepest points in the other 4 oceans. Crewed subs are only part of the story. Most of the time, no one is on board. Japan's remotely operated vehicle Kaiko was one of the first uncrewed machines that could reach full ocean depth on a regular basis. In 1995, it became the second vessel ever to reach the bottom of Challenger Deep, recording a depth of about 35,800 feet and collecting mud and microbes from the trench floor. Kaiko made around 20 successful dives before a storm in 2003 snapped a steel cable during recovery, and the vehicle was lost in deep water off Japan. The United States built its own full-depth robot, a hybrid vehicle called Nereus. It could work as a free-swimming robot or as a tethered, remotely operated vehicle on a hair-thin fiber optic line. Nereus reached the bottom of Challenger Deep in May of 2009, down to about 35,700 feet, and at the time, it was the deepest diving vehicle in operation. 5 years later, in May of 2014, Nereus was exploring the Kermadec Trench northeast of New Zealand at around 9,900 meters, roughly 6.2 miles down. Contact was suddenly lost. When the support ship pulled in the tether, they found only twisted fragments. Investigators concluded that part of the vehicle had probably imploded under roughly 16,000 pounds per square inch of pressure. Stories like Kaiko and Nereus shape how engineers build the next generation of deep machines. Anything that holds people or electronics needs to be inside a strong pressure housing, usually made from thick titanium or special steel. Viewports on crewed subs are not made from plain glass. They are thick acrylic or crystal windows shaped and tested so they will not crack. Buoyancy does not come from open tanks filled with air. It comes from solid blocks of syntactic foam, a material packed with tiny glass or ceramic bubbles that will not collapse. Instruments are often carried inside hollow glass spheres or ceramic shells about the size of a beach ball. These spheres look delicate, but they can handle pressures that would crush a main battle tank. Control is another problem. A robot on a cable can get power and commands from the ship through an armored fiber optic line, but that line has to survive its own weight, the ship's movement, and any currents pushing against it along the trench wall. If the vehicle is untethered, it needs batteries and must talk to the surface through sound pulses, which are slow and easy to lose in background noise. At full ocean depth, almost anything that goes wrong can become fatal for the machine. A tiny leak in a connector can spray ice-cold seawater into electronics. A seal can get squeezed out of shape and fail. A thruster can inhale mud and jam. Add the constant squeeze of thousands of pounds of pressure on every square inch, and there is almost no room for error at all. Thanks for watching. Now check out the videos popping up on screen for more unbelievable stories.